I'd like to start with the definition of basis. So what is a basis? Well, a basis of a of a subspace W of Rn is a subset B of W that satisfies two properties. The first one is that B is a linearly independent set. And the second is that the span of B is all of W. Now, the question is, what happens with this set? What characteristics does it have other than the actual definition? Well, before we get into those details, let me introduce an example. So I'm going to take W to be all of R2, and I will set B to be the set of vectors 1, 0 and 0, 1. And first, well, let's answer this too. Let's see if this set B satisfies these two properties. There's really nothing to be checked on W being a subspace of Rn, as well. W is all of R2. Well, let's check this ones. First, B is linearly independent. How do we do that? Simple. Let alpha 1 and alpha 2 be real numbers and assume that alpha 1 times 1, 0 plus alpha 2 times 0, 1 is equal to the vector 0, 0. Well, from here we get the following reduced equation that says that alpha 1, alpha 2 as a vector is equal to the vector 0, 0. So alpha 1 is 0 and alpha 2 is 0. Well, there we go. We concluded from the assumption that this linear combination is equal to 0 that the coefficients alpha 1 and alpha 2 are also equal to 0. So we already checked this property. It remains to be checked that the span of B is all of W, in this case R2. So how do we check that? Well, we have to take an element from here, and we should be able to write it as a linear combination of elements from B. So let X be a member of R2. Then X can be written as a column vector x1, x2. But once I write it like this, we have that x1 and x2 can be decomposed as x1, 0 plus 0, x2. And that decomposition can be even extended to obtain x1 times 1, 0 plus x2 times 0, 1. And now it's very clear that this vector that we have here is a linear combination of elements from here. So that demonstrates that B is indeed a basis for W.